While studying DC circuits, we learn that Ohm's law describes the potential difference of a circuit based on its current and its resistance. In a simple circuit diagram, we would have a potential difference, which most likely is a battery, symbolized with a parallel plate system, integrated into a simple circuit with a resistor, and we would define the current as flowing through the wire from positive to negative. And what Ohm's law truly described was that I was proportional to V as a direct relationship and inversely proportional to R based on the material makeup of the resistor. In simple circuits, this is enough because most resistors are standard calculated values of ohms, or they are the purpose of the question. So what Ohm originally started measuring was controlling a set amount of current with a initial potential difference. He could describe the relative conductivity or the insulating characteristics of a particular material. That term he termed as resistance. Resistance, measured in ohms, which is often symbolized with a capital letter omega, is a holistic term that describes much more about the actual resistor than was originally let on. And this leads us now to a discussion of a new term, which is deeper into the system. So let's use an example in order to get started. If I had a particular wire and I intend to carry current through the wire from one end to the other based on some sort of potential difference applied at either end, then how the current flows through the material does depend on what the material the wire is made out of. As an example, it could be made out of copper, it could be made out of gold, it could be made out of aluminum, it might be made out of something less conductive like plastic. However, not only does the material matter, also the physical dimensions of the given resistor matter. Now, in this case, we're using a wire, but all materials have some intrinsic internal resistance, and a wire is a good way of rationalizing this relationship because we can change dimensions and think about how this is working. Remember that I is the flow of electrons, and so if we think about this as being a crystal lattice of metal where the atoms are very organized in the system, then the electrons flowing through the system have to make their way past all of the nuclei of the individual material. So if I increase the space for those electrons to travel, then it stands to reason that the current would increase as well, or at least be capable of moving faster, which means that when we move from a smaller diameter to a larger diameter, the resistance actually decreases. And so what we see through a simple experiment here, and you could test this in a number of ways, is that R is inversely proportional to the cross-sectional area of the material through which the current is flowing. However, it stands to reason that no matter what the physical diameter or the cross-sectional area of the opening through which the electrons will flow, the electrons are inevitably going to collide and interact with atoms and nuclei as they flow from one side to the other. And so it's important to recognize that if I were to extend the overall path length, where I make the length of the actual physical wire longer, then going from here, my original diagram, to this one, then we expect that the current might actually decrease due to the fact that as it collides, it loses energy, and the more length there is, the more likelihood or probability there is of those collisions, which means there is a higher probability of a reduction in current. And so in this case, we see that R is directly proportional to the length of the given wire. Now, of course, this only incorporates the physical dimensions of the given wire, how long it is, and the cross-sectional area through which the current can flow. The last thing that Ohm measured, of course, was what happens when I change this from aluminum to copper to carbon to germanium to silicon, some of these semiconductors that carry current differently. And what that is all to say is that each individual material, element, or other has a different chemical composition of how the atoms are organized within the crystal structure. And so the overall flow path is different and can change from, say, copper to something more like germanium or silicon, which has a much lower ability to flow current. And so I would reduce considerably when going from copper to silicon, all other dimensions being equal. And this is where Ohm defined the term resistivity. Resistivity is defined as a material's overall ability to conduct electricity. It's a material's conductive characteristics based on its composition. Resistivity is given the variable rho and is measured as ohms per meter. And so ohms times meters, megameters. And so this is truly our proportionality constant as we go from one type of material to another, from copper to silicon or from copper to gold, etc. Right? And so putting these things together, Ohm was able to describe resistance as being a proportionality constant based on the material that it's made out, now we know called resistivity, directly proportional to its length and inversely proportional to its area. This formula describes how we would determine the overall resistance without actually measuring the current based on a potential applied to the system. And so this gives us a way of defining the resistant characteristics or the insulative characteristics. It should be the material's insulative characteristics based on its composition. This resistance is often applied to fairly symmetrical situations or devices such as wires, where the area would generally be the cross-sectional area of a round wire, and so there you would be looking at pi r squared. But it's not unreasonable for it to also include different size objects or different calculations based on some basic geometric shapes. One example that is applied in your textbook is to imagine a three-dimensional rectangular space. One useful study of the change in resistance based on how the dimensions change is to use a rectangular solid of metal. Let's say that this would be a block, a rectangular block of copper, C-O-P-P-E-R or Cu. Copper has a resistivity of 1.68 times 10 to the negative 8th ohm meters. And so this describes the physical characteristics of the material itself. However, if I have a rectangular solid, the direction through which the current flows makes a major difference in terms of the overall resistance. When I look at R equal to rho times L over A, if I took, let's define my axis as this is the x-axis, this is the y-axis, and then our third axis would be the z-axis. Suppose that moving through the z-axis, I have a current that runs the length this way along the z-axis through this solid. Then this face, which is x times y, is the cross-sectional area that will be used here. And this length, which is in the z-plane, will be the length. Now, obviously, this is a relatively small cross-sectional area in comparison to the dimensions that I've drawn here, and this length is one of the longer lengths. So we would expect that in the z directional plane, this current would be considerably smaller than, say, a current that would be running straight down through the top face, where this becomes A, and then the length would be the length or the height of the system along the y plane. In this case, the cross-sectional area is much larger, the overall path length is much shorter, the material stays the same, copper stays the same, and so we see that the resistance can change based solely on how this resistor or this conductive block is integrated into an electrical system. It's also possible for you to have multiple materials in a single connection. So one possible question would be, suppose a wire is composed out of one material that then seamlessly connects into another, where I have copper on one side and, say, aluminum on another. Assuming the dimensions stay the same, we would presume the current would flow through the wire in this direction, where I would have a cross-sectional area equal to the cross-section of the wire, and then, of course, the length. But, of course, if I'm switching from copper to aluminum, then the physical length for the copper would be here, call that L1, only to where the transition face is between the copper and the aluminum. And then the secondary length, L2, would be here through the aluminum, which means that a composite wire like this that's made of two materials would have a resistivity due to the copper and a resistivity due to the aluminum. So even though the dimensions stay the same, the resistance changes as we transition from copper to aluminum. In this case, you can think of this wire as essentially being a series connection of one resistance combined directly in with a secondary resistance, where R1 would be a result of the physical dimensions A, L1, and then the resistivity of the copper, and then R2 would be the resistance based on the physical dimensions L2A, and then the copper, or excuse me, then the aluminum resistivity. These would be connected in series because, of course, the current flows directly along through, and both systems would contain the same current despite having a difference of resistance.